Hello, we are Jürgen
and Joe
from SOFiSTiK. In this video we would like to show you how to insert hangers force-free. Now, what do we mean with this? When we have a little suspension bridge, we ship our last segment to site and then lift it to the final level, but then lift it a little bit higher so that we can then insert the hangers force-free. Now, as we do not want to re-stress our hangers later on, we have to insert the hangers with the correct length for the final system. To get this unstressed cable length, we first make an optimization on the final stage, as shown in the well-known example Optimize CSM20. This bridge here is in the folder More Opti CSM Insert Hangers. As we want our bridge to be straight at traffic opening, we have the target UZ equals 0 at node 20 and UZ equals 0 at node 40 and so on. And on every place we have a scalable load case, here load case 101, shortening the hanger to reach this target. So 5 scalable load cases, 5 targets. We have here our bridge. We first make a load case with an estimated pre-stress, and we get here a lifting of the main span. Now we start the optimization, and we see that after some steps the deformation of the bridge deck is really 0 for the state. But we see that here our hangers are not vertical, they are going a little bit to the left. So what can we do? Now, Jürgen, that is quite easy. We make a scalable load case where we shorten this main cable part and lengthen this main cable part. And with this we can easily reach a target that the deformation UX at this node shall be 0. The same we do on the other side. If you have a curve bridged, you can also define a vector UX, UY, UZ for this optimization direction. Also, we found that the bending moment on the pylon was not exactly 0, so I inserted a load case 192 that is shortening only this main cable part, and with this we can adjust the deformation UX at this node 31 to be 0. If you have a cable stayed bridge, you will also get the following problem. In the optimization on the final stage, you get a normal force in your superstructure. This normal force leads to a shortening of the superstructure, and therefore the two pylons are bending together. So you can also insert a scalable load case, here 199, with an elongation of the closing gap part. And with this scalable load case, you can adjust maybe the deformation UX on the top of the pylon. When we now run this optimization, we get a perfect stressed bridge on traffic opening, and the hangers remain vertical. If we reduce the amplitude to 1.0, now it looks perfect. All right! When we open WinGraph, we can find in the results the cable element relaxed cable length. So this hanger must be prefabricated with a length of 7.643 meters. We now come to the staged analysis. We first activate our pylons, then the side spans, then the main cable, and then the hangers on the side span, and then the derrick maybe. When we insert our cables in CSM, staged analysis, there is a command control ASE text len 0. With this, we tell the program that whenever a cable group 21 is inserted, it shall be inserted with the length of the cable that had been calculated in load case 1001. And that was our final stage analysis. We now define our construction stages 10, 20, 30, 4, 31, and you see it is very nice to use this feature here. Whenever maybe we activate group number 13, it is not necessary to define the stage of activation, ICS1. When you place this line here after this stage, so automatically the group 1 and 13 is activated at stage 20. Also with the load cases, you can just define here a load case, and then this load case is first activated in stage 140. Now we come to the stage activating the last segment in midspan. You see, I have used here a trick to make the visualization nicer. I activated 10 meters below, then lifted 5 meters, lifted 5 meters more. Then comes an additional lifting of 3 meters to insert the hangers force-free in the next stage. Now, how do I define this? Here is the lifting technique for the last segment. You see we have our stage 110. We activate some groups and some load cases, and then I define control ASE 110. With this I can give a text to the ASE calculation that only activates in stage 110. And this is a launching of group 2 by dz equal minus 10 meters. That's a technique from our incremental launching technique. In the next stage, I only shift the segment by 5 meters. Then I remove the launching. That means that it is in the original position. And then in the next load case, I lifted 3 meters more. But this is not done by a launching, because when I activate the hangers in the next step, it is not possible to activate the hangers in a launching position if you want to activate the hangers with a given unstressed length. Now, the next step after inserting the last segment is to slacken these lifting cables. So here are lifting cables, and I lengthen these lifting cables now, and you see, lowering the midspan, we see that the main cable and the hangers now come into tension. Now we have the problem that the additional dead load is not yet activated on this part, and therefore our last segment is a little bit too high. So what can we do here, Joe? Okay, we make the same things as we would really do on site. We install an additional part on the bottom. We pull down the bridge. We pull down here this cable, and then we can weld it together with a perfect alignment. In the input, we make a stage 182, where we shorten this cable to pull down the mid part. Then in the next stage, we activate an additional cable and pull it with a load case. And then we weld it together. That means we activate our group 4 that represents the small gap. So in SOFI load, we define a load case 20,182, where we pull this cable number 71, that is this cable here. But how do we get this value? First, we make an estimate of 400 millimeter. Then we activate SOFI load. In the CSM we can write, please only run load case stage 182 with this control test. And if we run this with calculate, you see it is very, very quick because it is only one stage. We can now look to our animator, amplitude 2, and we see the pulling down here was 400 millimeters, not enough. So we go back to our SOFI load, we test maybe 1500 millimeter, we calculate everything very quick, look to the animator 182 and we see this was too much. Now we of course take 1000 millimeter, run it again and look to our result with amplitude 2. Pulling down, you see, not bad. And we now make a last adjustment, 1030. We run it. And if we now look to our result, we see amplitude 2. That was the stage. Pulling down, we really got here the same height, left and right, with a manual iteration. The advantage of this manual iteration is that you get a good feeling for your system. Of course, you can also make an automatic optimization run with CSM Opti, but it is a little bit more complicated. But in the input file, you can find it at the very end. Okay, thanks. Now we do the same on the other side. We install an additional mechanism on the right side. We shorten the gap a little bit, we pull down the midspan. Now we pull down this cable to get the correct tangent of our bridge. And then we can weld it together. Then we can remove the direct. And now we can activate the additional dead load. And when we now activated the additional dead load, I click here to this point, number 50, we can really see our deformation is nearly 0, only 10 millimeters. A short comment to the horizontal correction. We closed our superstructure and afterwards we apply the additional dead load. This gives a sort of arc behavior. We get here a compression in the support and a compression in the superstructure. To avoid this normal force on traffic opening, I have inserted a little load case here that applies a tangent to the superstructure before closing. Then we close the gap. We have the tangent normal force in the system, and when we then apply the additional dead load, the tangent is eliminated and we do not get any normal force at traffic opening. This, of course, only appears when you have here a fixed connection between the pier and the superstructure. Now we come to our final traffic opening stage, including the staged analysis, and you see we have a very nice balanced bending moment in the superstructure. The deformation of the superstructure is nearly 0, and with this we can open our bridge. So, thanks for listening and goodbye.